Good morning, good afternoon, good evening. Welcome to the Combustion webinar. And my name is Tigang Fang from North Carolina State University. And today is our great pleasure to have Dr. Daniel Mira to give us talk about high fidelity simulations of multi-physics processes in aeronautical combustors. And Dr. Mira is the head of the propulsion technology group at the Case Department of the Barcelona Supercomputing Center. And Dr. Mira received his bachelor's degree from the Polytech University of Valencia and in 2008, and his PhD from Lancaster University in 2012, and both from mechanical engineering program. And his research is mainly focused on the development of advanced simulation methods, mainly to study the combustion characteristics of propulsion and power systems. And his main current activities, including the development of physical modeling and numerical methods using high-performance computing and data-driven approaches. So with that, let's welcome Dr. Mira. And it's all yours, Dr. Mira. Please go ahead.
Thank you very much for the kind introduction, and thank you for the invitation to participate in these interesting webinars. So today I'm going to talk about the research that we are conducting at BSc in our group about the modeling and simulations of combustion systems for aeronautical combustors. So before I get started, I would like to present who we are. We are the Barcelona Supercomputing Center, which is the national supercomputer facility in Spain. We are located in the northeast of the country, in the city of Barcelona. And BSc is a large institution dedicated to computational methods for all type of physical and engineering problems. We work in the engineering department, and then we have quite close ties with the Mare Nostrum supercomputer that is hosted in our institution. So Mare Nostrum is a supercomputer tier 0 from Europe, which means that it's in the group of the largest supercomputing infrastructures that we have. Now we are in the process of waiting for the next supercomputer, Mare Nostrum 5, that will be in operation at the end of this year. So just more focused on the presentation, as people working in combustion are very aware, there are current trends in aviation towards the reduction of the pollutant formation and also the decarbonization dependency that we have in these power and propulsion systems for aircrafts. So there are regulations that coming into play and some objectives given by ACARE that are targeting important reductions in CO2 and also pollutant formations like NOx and noise. Besides this, there are regulations coming about the integration of sustainable aviation fuels in current engine technologies that meant to be in 20% of SAF composition in the jet fuel by 2035 and 40% by 2050, and also regulations about the non-volatile particulate matter that are also coming for 2023. Non-volatile particulate matter for combustion engineers means soot, and this is one of the main challenges that we have in our community. So in order to address these current intentions of decarbonization and increase efficiency, there are fundamentally two different directions. The first one is the integration of alternative and sustainable fuels into current engine architectures. For instance, the use of sustainable aviation fuels and also the use of hydrogen in aero engine architectures. And then on the other side, we have this development of new combustion technologies that can change the current paradigms in terms of emissions, acoustics, and efficiency. So along these two lines, I would like to focus my presentation of today, trying to give a little hint on how numerical simulations can contribute to address these problems. So it is important to say that combustion is at the central part of these two strategies. And this is why it is important to keep working on combustion and to keep trying to understand the complex phenomena that are still to be resolved. So in fact, what we are interested in is to increase the efficiency of the aero engines. The problem is that these systems are very complex, are very large, are operate at very demanding conditions, and it is difficult to make a understanding on fundamental problems directly from these systems. So in fact, it is quite challenging for experiments and numerical simulations to actually address the problems that occur at the engine. So this is why a lot of effort is dedicated to develop experiments and simulations where the boundary conditions are quite well established and well identified, so we can isolate the phenomena that we want to investigate. So this is an important aspect that experimentalists are been doing for many years, and now it is important to address this part because we have new challenges coming from the fuels and the new combustion systems. So it is only after we understand the physics of combustion where we should be able to develop models and how we should be able to integrate modeling tools and computational models into the design and operation of these engines. So this brings to the outline of my presentation. So in the first part, I will try to describe quite briefly some of the important elements that are required to conduct high-fidelity combustion simulations, mainly in the context of complex geometries and realistic engine applications. Then on the second part, that very short, I will just try to map what are the challenges that we see in the integration of these new technologies for aviation, and then the relevant phenomena that is associated to this. So based on this, I will then focus on three particular applications that we have been involved and trying to address the problems that I have just mentioned. Finally, I will end with some conclusions and some directions for future work. So as a start, let me give you quite a brief overview of the combustion physics that we are trying to target in combustion systems. So in fact, after in general, the fuel that is used for aero engine is currently liquid kerosene for most of applications. And then this fuel has to be injected into the combustion chamber. Then it is usually at high pressure. Then in this case, the fuel has to atomize from the liquid vein. It has to break into ligaments, filaments, and then eventually into droplets before the fuel can be evaporated and mixed with the air. So in fact, we have important challenges because this atomization process is quite complex, and it depends on scales and conditions that are quite challenging for numerical methods. Then on the other level, what we have is after the fuel and the air are come together, then we have to describe the ignition and combustion. And then this is quite important because different fuels will have different burning characteristics, and we have to deal with this. And this is why the description of chemistry becomes very relevant. Even more important for pollutant formation, chemistry is the dominant effects, and we need to accommodate reaction mechanisms with CFD calculations, so we can actually address the realistic problems happening in the engine. Besides the turbulent and the chemistry interactions that usually occur as scales that are smaller than the mesh resolution that we have, which at the end brings a lot of requests for the numerical simulations, because we have to deal with a multi-scale and a multi-physics system. And then if we are interested in looking at realistic engine conditions, we have to rely on techniques that are high fidelity, but not extremely computational expensive, which LES stands out at this level. And also combined with high performance computing and algorithms. So at the end, with the incoming power in the supercomputers coming from the exascale next generation supercomputing architectures, combustion will be extremely benefited, and this will bring us the opportunity to address problems that we have not been able to do before. So in general, when you are interested in achieving combustion simulations, you have to address three specific elements altogether. The first one is the physical models. We need to have appropriate models to describe the flow physics that we want to resolve. On the second place, we have the numerical methods. We need to resolve these equations with a control level of accuracy at least. And then finally, we have to integrate these methods into algorithms that could allow us to solve these equations efficiently and also at a reasonable cost. So going a little bit deep into numerical methods, we can consider, for example, the transport equation of a chemical species that is described by this expression here. What we see is the classical hyperbolic problem where we have the temporal term, the convection term, the diffusive flux, and also the source term. So I believe that all the researchers in combustion are familiar with this type of equation. But then how we solve this equation, this can change very much. So we have a variety of methods that can be used to solve these equations. And then depending on which method we use and we select for solving this problem, we are going to get different results. So we need to be careful, and we need to identify what they are the requirements of the numerical methods that we are interested in. At the end, we have to select methods that are globally conservative. So we want to conserve properties like mass, energy, and momentum. But we also want our schemes to be total variation diminishing. So we don't want to have overshoots in our combustion simulations that are very troublemaking for making divergence in our Arrhenius expressions and other aspects of the simulation. And also, these methods have to be integrated in parallel algorithms. Otherwise, we will not be able to solve the problems we are targeting. And of course, if possible, we would like these methods to be fast. So we don't need to wait a lot of time for our simulations, but also we don't need so many computational time and resources. So just going on this direction and try to highlight the importance of numerical methods, if we consider the same transport equation for a chemical species, and then this is the continuous form of this transport equation. Basically, most of the researchers working in combustion solve this equation exactly as I posted here. However, in fact, when we use numerical methods, we solve a discretized form of this equation, which means I represented here by the weak form of this equation. And then depending on the numerical method that you use, for us, for example, at BSc, we use the finite element method. This equation is discretized using piecewise linear subspaces. And at the end, if you look at the first equation on the top, and then you compare with the equation on the bottom, you can see that these equations are very different, which means that when we implement these equations in our CFD codes, depending on the method that you use and how you implement these equations for the same physical model, we can end up with different results. So I'm trying to give you an example on what are what will happen in some cases, depending on the method that you use for solving these equations. For instance, when we develop our low-Mach solver for our code, we wanted to evaluate what is the influence of the convective operator in the momentum equation, that we know that it's a critical term that can contribute to bias your solutions by adding dissipation in regions that they are not meant to. The convection operator does not should not introduce any dissipation, and the only dissipation should come from the diffusion term. So in this case, what we did is that we compared two different approaches for the convection operator, the classical skew-symmetric that conserves the kinetic energy, and also with a EMAC, which is an energy conserving but also momentum conserving algorithm. And then we applied these different closures on the convective term for solving some specific reacting flows. We started with a jet flame, a simple jet flame from the ISF workshop. And then what we could see here, you can see on the top, you can see the axial velocity at different axial locations. In the middle plots, you see the mixture fraction, and in the bottom, you see the temperature. What you can see is that depending on the discretization of the convective term, you can end up with different solutions on your flow field. In this case, in the jet flame, it was especially relevant to see that this EMAC formulation was able to further maintain the momentum on the jet, which was very important to achieve good results on this case. We also tested these different strategies on premix soil burner, and then we also obtained an improvement compared to the classical skew-symmetric operator. So with this, the takeaway is you have always to check your numerics. Your numerics can have a high influence on your results. So once you select the numerical method that you want to solve your equations with, then you have to define what methodology you want to solve for combustion. So let me just change a bit the nomenclature here, and let me represent the conservation equations for reacting flow with this classical expression. So in this case, one of the main limitations is when we want to solve this equation is how you deal with the chemical source term, because depending on the reaction mechanism, the computation of this term can result very costly, and this can introduce substantial cost in your simulations. And the other part is that if we want to go to large eddy simulation, we have to fill these equations. So how we are going to filter the chemical source terms? So based on this, a wide variety of turbulent combustion models have been developing in our community for many, many years. There are extensive reviews, books, and I will not go into the details of all these methods, but let me simplify the category of the methods, and let me separate them into what I call finite rate chemistry models. So in this case, from the transport equation of the reacting species, then we can define some operators in the convection and diffusion and the source term, and then we solve equations for all of the species, in which we will have to deal with the transport of all the species, but also with the integration of the chemical source terms. And then in the other category, let me introduce what we call tabulated chemistry method, which what they do is a simplification of the problem by changing the space of solution. So instead of solving the equations for all the species, we solve a subset of equations that represent the composition space of the solutions of the detailed chemistry, but by using only control variables that cover the whole manifold representation. So let me just go a little bit on this method, that this is the one we use for our simulation. So in general, tabulated chemistry method are based on a series of steps. So in the first step, what we do is the generation of our flamelet database. So basically, depending on the kind of configuration we are looking at, maybe we can consider that the premix flamelets can better represent the flow characteristics. For instance, in a premix flame or premix flames with equivalence ratio fluctuations. Or on the other hand, if our flame is better characterized by the diffusion of reactants, then we can do our tabulation based on the 1D counterflow diffusion flames. Other configurations are possible, and this is at the moment an active area of research. In the second step, what we do is from these 1D simulations, we construct our flamelet manifold. So we transform the coordinates of the physical space into the composition space, and we tabulate the properties of our 1D solution as function of certain controlling variables. Because we are solving our equations in 1D, we can perform some statistical integration of the equations, so we can incorporate statistical methods in the manifold still in a pre-processing stage. So for instance, flamelet methods are classically used with presumed shape PDFs, and then this will permit to integrate all the species into the PDFs and tabulate this in a pre-processing stage to build the lookup tables. And then in the final step, what we do is we run our CFD simulations, we transport the equations for the controlling variables, and we recover the properties of the manifold directly from the coupling these tables with the CFD. This method that results quite interesting and quite efficient, because we have to solve few transport equations to represent the whole combustion problem. Then it also has some limitations. The first one is to how we can deal with the multi-regime conditions in this kind of simulations, how we can store databases that can represent with high fidelity what happens in the manifold. And these are the kind of questions that combustion researchers are looking at the moment. I've seen that there are new developments to address multi-regime conditions, and we are looking forward to understand and to develop these models and see how they can be applied for these problems. In particular, I would like to bring the attention to the table to management of the flamelet databases. We've been looking into an approach to store large databases, but instead of storing the databases by the computing node, we store all the databases using remote memory access. So each of the computing nodes will only store a small portion of the table, and then during runtime, if they need information, then they recover the information through the other computing nodes through MPI. We have been testing this, and this seems a good and efficient way to incorporate very large flamelet databases into flamelet calculations. So this will be presented by Nick Abel in the incoming weeks in the next Parallel CFD conference. So let me then go back to the problem we want to solve with these methodologies. So if you remember that we were trying to address how we can incorporate SAF fuels into current engine technologies, and also how we can integrate hydrogen. So for SAF, basically is considered at dropping in fuel. So we can use current combustion technologies based on RQL, LDI, limp premix combustion, and then to develop high TRL technology, because basically we need to integrate these fuels into the existing technology. In the case of hydrogen, the TRL, or the technology readiness level, is lower, so there is more exploration and more research to be conducted in how to develop a hydrogen injector that can be appropriate for aeronautical engines. So the problems that we face with SAF are classical problems that we have with jet fuels, but with the characteristics of the new properties and the multi-component characteristics of SAF. But in the case of hydrogen, there are numerous challenges that we need to deal now with. For instance, the blending of hydrogen with other fuels, flame stabilization, NOx formation, flashback, preferential diffusion. There are all these new problems that we have to face from going from traditional hydrocarbon fuels to hydrogen fuels. So in the context of this presentation, I will just focus a little bit on these particular aspects, considering some configurations that are in the literature and in some of the labs across Europe and the US and Asia. So at the end, let me just go back to some applications. So I will focus mainly on three configurations. The fuel stabilized burner from the Technical University of Berlin that is used for hydrogen combustion, the DLR model combustor from ISF from the DLR Stuttgart, and the recent experiments from DLR Stuttgart on the high pressure pre-Kinsta burner. Before going into the applications, let me just introduce our multiphysics code that is named ALIA that we develop in the department. Our code is a parallel solver based on finite elements, and it's been one of the main characteristics is that this has been tested in most European supercomputing platforms, and also outside Europe. And the code is developed in the way that we try to maximize the parallel performance for all these type of applications. So let me start from the hydrogen case from Berlin. So in this case, this is a fuel stabilized burner with axial air injection that has been designed at the Technical University of Berlin to operate with high flexibility under different type of fuels. We've been looking into this burner in the past in premix conditions, and now we are looking into the effects of fuel air mixing on the flame characteristics. So what is interesting about this burner can be seen on the stability map that I have put in the middle of the slide. What you can see is that if we move along the blue arrow, what we see is that the burner operates stable in the region from stoichiometric conditions down to equivalence ratio 0.4, where we enter into the flashback condition. So this burner exhibits flashback phenomena at low equivalence ratio. So after further reduction of the fuel, then we move to the limb blowout limit. So at the end, we have this region that flashback is produced that has been investigated experimentally by Thoralf and Paschereit in the TU Berlin. And we also wanted to perform some simulations, so if we could provide some further understanding of this mechanism. So first, we started, of course, in the CFD, building our mesh. Our mesh is in the order of 10 million nodes, with some refinements in the combustion chamber and also in the fuel injector. And then we started by looking at the non-reactive flow characteristics in order to predict the hydrodynamic behavior of the burner. What you can see here on the left is the comparison of the axial velocity from the LES with the experiments for the mean and the RMS. So in general, the agreement was quite satisfactory, and also as the burner was exhibiting a self-excited flow oscillation referred as PVC, we wanted to see if our simulations were able to recover these transient characteristics. And then for that, we compared the POD with experiments and the LES, and we found a good correlation on the Struhal number and also on the characteristic frequency of this phenomenon. So this was a quite important step before going to simulate the reacting flow field. So for this, we started considering a stable operating point at equivalence ratio 0.6, as you can see on the figure on the left by the blue dot. And then we found a quite good correlation with the experiments at all the axial locations. And then we did the same for the lower equivalent ratio at 0.4. So this was quite an important step to provide some confidence on the results before we start analyzing the flow fields. So here you can see the mixing characteristics of the burner. So the hydrogen is injected from the fuel injectors, and then the fuel is pushed to the middle by the swill that comes on the side. I don't know if you see my mouse, but here on the top figure is represented the equivalent ratios. On the fuel is pushed to the center, and then the fuel is then interacting with the axial air injection and the swirling flow, which leads to the quite degree of stratification, as you can see in the animations that you have in the bottom. So they show the equivalent ratio for the two test cases under consideration. Here you can see an animation of the flow characteristics for the two operating points. At the equivalence ratio 0.6, the flame is stabilized in the combustion chamber around the plane of the nozzle, and then the flow is characterized by the interaction of the vortex breakdown stabilization with the corner recirculation zone. So the flame is anchored by these two recirculations. On the equivalent ratio 0.6, the flame is stable and it does not move, while on the equivalent ratio 0.4, the flame starts to have some oscillations that moves and penetrates partially inside the mixing tube, but then it returns to the combustion chamber. So it is a stable operation, but it has some intermittency and some complex dynamics. As the equivalence ratio is further reduced, we move to 0.25, then the flame exhibits very complex phenomena that then it enters in the mixing tube, but then it gets out, and this is an phenomena that we are currently investigating. So I move to the second application that is about soot formation, and I consider this challenging case that is included in the International Soot Flame workshop. That are some experiments that were conducted at DLR by Klaus Peter in the context of several European projects. In fact, this case corresponds to the ISF target flame number 4, and it's operated with ethylene at a 3 bar. And in this particular case, we consider the oxidation air coming from those side jets. So for the simulation, well, I forgot to say this is a collaboration between our group at the BSc with the Technical University of Eindhoven and the CMT Motores Térmicos to try to develop advanced soot models for aeronautical applications. So the modeling approach on this problem is we are using a reaction mechanism developed by the University of Stuttgart in Germany that is mainly specifically developed for jet fuels. And we developed this in the context of the European project Estimate. And then we use flamelet tabulation by considering counterflow diffusion flamelets using Lewis number =1. We use a new formalism for the discrete sectional method with FGF chemistry that I will describe very briefly. And then we have a mesh in the order of 52, 54 million elements in the combustion chamber. So for this, we use LES with the subgrid scale Bremen model. So just to give a quick introduction of the SUD model, this SUD model was presented a few days ago in the International Conference on Numerical Combustion in San Diego in the US. And basically the idea is that we are trying to reduce the computational cost of SUD in flame calculations by developing a tabulated chemistry SUD modeling approach. So the idea of this method that I will describe very briefly is that we solve our flamelet 1D flamelets considering detailed transport and all the sections for the SUD model. In this case, what we do is we then retrieve and we create our flamelet manifold, but instead of tabulating the source terms for all the individual sections, what we do is that we group these sections into clusters, and we maintain the intra-sectional distribution of sizes within the cluster. Therefore, what we can do is take advantage of transporting only the clusters, and then during runtime, we can recover the original particle size distribution. So in this way, what we can do is to reduce the computational cost of transporting all the required sections that we need to have accurate prediction of SUD calculations. So for instance, in these simulations, if the original size distribution considered was 60, for these simulations, we only transport 6 clusters. So along 10% of the total number of the sections seems quite reasonable to obtain good results. All this methodology was presented in the conference with proper validation, and I encourage you to look at the abstracts and the papers. So going into the simulation, again, we consider a hybrid mesh with local refinements around the injection and mixing of the fuel with the air, and also the position of the flame, and also the position of the side jets. And here you see an animation of the axial velocity for this case. And on the right, you see the comparison of the axial velocity for different positions and along the center line. What we see is that the results of the flow fluid are quite well predicted by the numerical simulations, and it also happens the same for the temperature. In this case, we compare two solutions, one with the adiabatic calculation, and the other one including heat loss into the flamelet manifold. What we see is that in order to predict the correct temperature fields, it is important to account for the heat loss between the flame and the walls. So this is a preliminary step to get reasonable or meaningful results with the SUD model, as it is highly dependent on the temperature. Here I'm showing an animation of the SUD volume fraction on the left, and then some comparison with the experiments on the right. If we focus first on the animation, what you can see is that the SUD is produced mainly on the inner layer of the flame, and then it is transported downstream, and we see a small production of SUD near the central part, but when we do the time averaging, as you see on the right, there is not much soot predicted in the recirculation zone. But the shape, if you compare the figures on the right, of the soot formation is quite well predicted with the experiment, but the peak values that we have obtained are still over predicting the experimental values. So this is now for us an active area of research, and I hope we can bring more and improved results in the incoming months. So if we move to our third application, this is a collaboration that we started recently, well, already a few months ago, with the DLR Stuttgart with Dr. Isaac Box about the prediction of the prediction of the effect of the hydrogen enrichment into natural gas flames for aeronautical applications. So for this, we've been looking into the experiments performed by Dr. Box and his group at DLR, and we have been mainly focused on at the moment on the atmospheric pressure condition. Basically, in this investigation, we want to understand the effect of hydrogen enrichment on the flame stabilization for this particular burner. For these simulations, we conduct LES with the tabulation of laminar premix flamelets and using presumed shape PDF. For this, we use the GRI mechanism for all the calculations. So as a start, we consider the first, as always, the inner conditions. We perform a mesh in the order of 50 million cells, and then we try to resolve the flow characteristics. As you can see in the animation, this inner flow condition, but also the reacting flow, exhibits a precessing vortex core, which with a simple visualization of the Q criterion can be quite well distinguished. So we are actually at the moment trying to quantify the frequency and the mechanism of this hydrodynamic instability. But then we also move to the proper validation of the inner condition, and here I present the mean value along the axial direction of the combustion chamber at different radial positions. So you can see the correlation with experiments for the mean value is in quite a good agreement, and also for the RMS. The RMS is not the profiles are not totally smooth because it requires additional integration time and also some azimuthal averaging that we have not conducted so far. But in general, the results of the non-reacting calculation are in good agreement, which brings the start of considering the reacting flow. Then if we move to the reacting flow with 0% hydrogen enrichment, I'm presented here the mean axial velocity of the simulations compared to the experiments, and we see that in general the agreement is quite satisfactory. So the simulations were able to predict the formation of the central recirculation zone and also the intensity of this recirculation. Besides that, the peak values of the axial velocity are still over predicted. At the moment, this is being improved by running with a finer mesh that we believe that is going to improve the Fuller mixing, and then it will impact also on the propagation velocity of the flame and the axial velocity distribution. So we see here also that the RMS are also in quite good agreement. So this shows a good promising strategy for looking at these configurations or these test cases from this partner. So in this case, if we look a little bit closer into the burning characteristics of the flame, what we see here is that the flame on the left, it's presented the heat release, And the temperature in the middle is the mixture fraction, and then on the right is some scatter plot that shows the burning region of the flame. What we see on the figure on the left, on the video on the left, is that the flame is totally detached in this burner, which was quite well predicted by the numerical simulations. This is considered in this case that is referred to M-shaped swirl flame, and this flame dynamic is quite well reproduced in these simulations. Then if we look at the figure in the middle, we see that the mixing is quite heterogeneous. We have very rich and very lean pockets coming out of the nozzle, which introduces a lot of challenges to flamelet methods to recover the flame propagation in such conditions. But if we look at the scatter plot, what we see is that the flame, it's burning in a quite wide range of equivalence ratios, going from 0.71, which is the global equivalence ratio in the experiment, to 1 or almost 1. So it is quite a wide range. And in our case, the central part of the burning is shifted more toward the rich side, which could explain why the peak velocities are slightly overestimated. Of course, this is a part of our effort at the moment, try to predict a better mixing and to understand if this is the mechanism of this deviation. But considering the different limitations and the different possibilities of flamelet tabulation for this kind of flames, we have started to look into the different hydrogen enrichment. What you see on the figure on the left is the flame that has 0% hydrogen injection, and what you see is that the flame is completely detached of the burner. Then if we move to the case in the middle, we see that when we include 40% hydrogen, it is considered in the experiments as a transitional case. So the flame is detaching from the burner, but in other moments it gets attached. And then on the 50% hydrogen in the experiment, the flame is fully attached, and these simulations were able to predict this configuration. What we can see is if we compare the 40% and the 50%, there is a lot of oscillation of the flame attachment to the wall that is moving around the conical nozzle, which indicates that indeed at this operating condition, the flame tries to detach in this case, while in the case of 50% hydrogen, the flame is more attached and more stable. So indeed, we can conclude that the simulations were able to predict the transitional evolution from N shape at 0% hydrogen to V shape at 50% hydrogen. So with this, I come to an end of the presentation, and I would like to give just a few takeaways. So the first one is that if we want to address or achieve high fidelity simulations with LES and even DNS, we need to define appropriate physical models, but not only physical models, but also numerical methods and HPC algorithms, so we can try to address more realistic problems, and also with a quite trade-off between accuracy and computational cost. The simulations involving hydrogen and submodeling are quite challenging for the current state of the art of computational methods. And despite that there has been significant advances on this field, still we face many challenges for the research community. The first one is that if we want to stick with the reduce models for turbulent combustion, we need to address the multi-regime characteristics of these flamelet methods, and I see that there are many attempts in the community to look into these models that have a lot of potential for looking at complex and high pressure conditions. Then if we want to correctly reproduce the flame propagation, we need to include preferential diffusion in our simulations. And the same for the soot. We need to incorporate multivariate soot models so we can consider a more realistic description of the physical phenomena of soot formation. Then as an end, just to say that the supercomputing architectures and the incoming increased computational power that will be available to our disposal for combustion simulations, it is a good opportunity for the researchers in this field to try to address problems that have not been able to solve before, and now we have the mechanisms that we can try to address them with a certain, let's say, robustness and well, control of the error that we have. And with this, of course, I would like to thank all the people that have contributed to this presentation and the results of this presentation, code developments, and all the levels, and also external collaborators that have allowed us to do interesting research on this field. And with this, I would like to thank very much the sponsors and the organizing committee of the webinar for allowing me to participate. Thank you very much, and I'm happy to take any question.
Okay, thank you so much, Dr. Mira, for your excellent talk. And we have some comments and a few questions in the chat box. I think we can just start it based on the order we received them. So I think the first one from Dr. Gore, just kind of some comments. So I would like to say what Dr. Mira will say about this. So based on the recent webinars and the recent publications in many international journals, shall we say that the LES and subgrid scale models based on non-premixed, partially premixed, and premixed flamelet-based libraries and databases of various kinds include MPI and even including machine learning and AI have become kind of standard practices around the world, and we can all benefit from simply documenting this well and comparing the regimes in which they work well or do not work so well. So do you have any comments on this?
Okay, well, it's a very interesting comment. In fact, this is the reality, and just to be honest, I just come from San Diego, in which I first time a conference after 3 years of COVID, and I could see really quite a lot of progress on machine learning for subgrid modeling, for combustion chemistry, and new advanced turbulent combustion models, mixing finite rate chemistry with flamelet models, which I think is really impressive and quite relevant for this application. So I think that considering the conventional one-dimensional space in flamelet models can be now relaxed and extended using these new formulations that are very powerful and also can allow us to represent better the physics of the flames. Indeed, this is really something that we are all going to benefit in the incoming years.
Okay, thank you, Dr. Mira. Next question is like, what the models were used for primary and secondary breakup of spray formation? And well, I think there's a little bit misunderstanding about your slides, maybe. Yeah.
Yes, well, yeah. So sorry if there was some misunderstanding. So in reality, the presentations that I included today, I think I did not include in detail any spray flame, but for the spray flame that I show at the start of the presentation, this was done with Lagrangian particles. So I did not include any atomization primary breakup model. So primary breakup models are indeed very important for spray flames. We need to get better joint PDFs of particle sizes and velocities, so we can integrate them with Lagrangian particles for these spray simulations. But in my particular case, unfortunately, we don't have work on primary breakup.
And also, okay, ask what simulation software you were used.
Okay, for the simulation that I presented here, for all the results, we use our in-house code that is named Alia, and this is a platform that we have implemented and developed all the models. We have different modules with different physics for Lagrangian particles, for finite rate chemistry, for tabulated chemistry, multi-physics coupling. So we have a wide variety of methods available in the code, and then we apply them for the target applications.
Okay, next question for the second application. What is the fuel, and is it premixed or non-premixed combustion?
This is an interesting question. For the second application for the DLR aero engine model combustor, the fuel is ethylene, and in this case, the characteristics of the combustor are complex because it's not either premix or non-premix or diffusion. So it's non-premix, and you have a wide variety of regimes taking place in the flame. So for our particular approach, we consider that for the variations in equivalent ratio that we observed and the amount of air that is introduced in the burner, we proposed to use the tabulation of counterflow diffusion flames to address this burner. And we found that indeed this was quite acceptable to predict the flow fields in terms of velocity, temperature, and eventually primary zones of soot formation. But indeed, it is clear that, of course, the diffusion flamelets will have certain limitations to predict the flame propagations in regions where the fuel and air are homogeneously mixed and they propagate into the chamber. But considering these limitations, we have seen that this approach is quite valid to represent the flow condition in the burner.
Okay, thank you.
Well, sorry, I forgot to say, just to provide a comprehensive answer. In fact, what we do is we tabulate the stable branch of the S-curve, and then to account for local extinction, what we do is we, from the extinction point, we tabulate an extinguishing flamelet that goes from the extinction point down to the mixing line. So we can recover the whole manifold from mixing to combustion.
Okay, so next question is, what are your considerations about the influence of using adiabatic FGM, and Lewis number is 1 for the CFD model?
Okay, well, a good question. In fact, we want to include all the physics. We wish we could include all the physics, but the way we do it is we are integrating the physics step by step. So in the first, the DLR combustor, if you don't include heat loss, the temperature that you get is usually quite off, which will have a direct impact on emissions on pollutant formation. If you are interested in the hydrodynamic behavior of the burner, maybe the heat loss is not the first, it doesn't need to be your first choice. There are other things that you could improve before you integrate, let's say, the heat loss on your flamelet model. So for the pre-Kinsta burner, in fact, we are now incorporating heat loss into the flamelet manifold to account for this effect that it is known that is going to have some effect on the flame stabilization. And about including preferential diffusion for hydrogen in chemical manifolds for FGM, indeed, this is now an active area of research. It was discussed in many sessions in the numerical combustion conference, and now there are we are now in the process of integrating some of these approaches in our code. And indeed, this is an important element for these simulations, and I hope that we can show some results of this very soon.
Okay, as the last question, kind of a group question from Dr. Gore again. So about the shooting flames. So how do soot particles diffuse? Is thermophoretic diffusion considered, or is radiation considered in these flames?
Yes, in our case, we are included in the governing equations for the soot thermophoretic term. However, we have not really checked this properly, but in the turbulent flame, this might not be the dominant effect. But indeed, we have a term that accounts for the thermophoretic velocities, and also we have a term that we are now plugging off in the turbulent flames that introduces some numerical diffusion for the soot that it is relevant in the laminar cases, but is not so relevant in the turbulent cases.
Okay, yeah, thank you so much. I think that's all the questions we received so far. And we thank you, Dr. Mira, again, and also thank you, everybody, and enjoy your weekend. So see you next time.
Thank you very much. Bye-bye.